Hello everyone, thanks for coming. Today we are going to do a review of our week 12 ODE course. So in this week, we talked about how to solve more complicated homogeneous linear systems and non-homogeneous systems, as well as numerical methods for solving ODEs. So for a linear system, x dot equals to ax, if the coefficient matrix A is not diagonalizable, then we need to consider its Jordan form. Suppose A is similar to J, where J is a Jordan form of the matrix A, then J is nearly diagonal. Eigenvalues of A appear on the diagonal, and ones may appear on the superdiagonal for this Jordan form J that accounts for repeated eigenvalues with insufficient eigenvectors. So if we convert A in its Jordan form, then we can show that y dot satisfies y dot equals to jy. So we can solve for y repeatedly, starting from yn to yn1. After solving for y, we can use the transform x equals to ty to get x. But of course, the calculation is more complicated than the case when A is fully diagonalizable. Specifically, if we combine those linearly independent solutions together to the equation x dot equals to ax, the way we would get the fundamental matrix P(t). We can show that P(t) equals to the transformation matrix T multiplied by the matrix EJT, where the matrix EXPJT can be computed via series expansions or Jordan decomposition. J here is the Jordan matrix. So this allows construction of the solution for the original system for any initial value problems. Specifically, for n greater than or equal to 3, eigenvalues may have high algebraic multiplicity but much lower geometric multiplicity, and the Jordan matrix can be more complicated. Repeated complex eigenvalues may occur if the dimensionality is greater than or equal to 4. So in those cases, we may need to use a calculator for calculating the eigenvalues as well as the Jordan form of the matrix A. So finally, we talked about how to solve the non-homogeneous linear system. Suppose we have x dot equals to px plus the non-homogeneous source term g. The general solution to this first-order linear ODE is x equals to the homogeneous solution plus a particular solution to the non-homogeneous equation. So how can we get the particular solution? We can make an analogy to how we get the particular solution to non-homogeneous second-order ODEs. Basically, there are different methods like the undetermined coefficients. We make a guess for the solution, for the particular solution, and then we try to solve for the coefficients. Diagonalization, that is to convert the matrix P into a diagonal matrix if it is time independent. Variation of parameters, that is to suppose x equals to P(t) times ut, where P(t) is a fundamental matrix to this homogeneous system. Of course, the variation of parameters methods highly depends on whether we can successfully solve for this homogeneous system. Finally, we can also consider applying the Laplace transform for vector functions, but this is more complicated than the Laplace transform for scalars. So to be more specific, different approaches are applicable to different types of problems. For the undetermined coefficients problems, it works very well for constant p and a simple function for the source term, like polynomial, exponential, or sinusoidal function g of t. For the diagonalization method, we need to find the transformation matrix that can transform the constant coefficient matrix A to a diagonal or Jordan form. In that case, we can solve the uncoupled first order ODEs, and then we apply the inverse transform to get X. For the variation of parameters, we need to first solve for the fundamental matrix for the homogeneous equation in order to get the particular solution. So the application of this method is kind of restricted in some cases. For the Laplace transform, this applies for any initial value problems, but and is extremely useful when the fourth term is discontinuous or impulsive, but the calculation is also kind of complicated. Finally, in this week, we briefly introduce the numerical methods, the Euler's methods for initial value problems. Suppose we have the initial value problems. We have two different Euler formulas. The first is called the forward Euler formula, yn plus 1 equals to yn plus a time step h times ftn yn. The second is called the backward or implicit Euler's method. So technically speaking, the backward Euler's method would require more calculation, but it's also more stable, which will be introduced later. So there are different sources of error. One is called the algorithmic error, induced by using the approximate formula because we need to truncate some higher order terms. Finally, the second type of error is propagation of previous errors. Errors gets accumulated if we advance time. Finally, since we are using the floating number calculation, there could be finite precision arithmetic errors, which is also known as a round-off error. How can we estimate the error? So basically, there are local truncation error. There is global truncation error. The local truncation error discusses the error that comes from using different sorts of numerical algorithms, like the Euler's algorithm. So for the Euler's method, the local truncation error is proportional to the square of the time step, and we can choose a step size to bound this local truncation error. For the global error, the global truncation error for the Euler's method is a constant times the time step. So that is to say, the Euler's method is a first order method. If we decrease the time step, the global error is going to decrease linearly with the time step. So the global truncation error can be derived from this local truncation error, and they also may require some additional stability conditions. Thanks for listening.